right. So welcome, guys. This is the first lecture of the blockchain course that we put together. And before we start, just want to give you a little introduction to the society and the people behind it. So the course is organized by Decentralized Society. We started last year in September, but it was, started with Victor, who's like managing the live stream right now, and me. And the whole purpose of the society is help you guys explore anything related to decentralized technologies, Web3, cryptocurrencies, DAOs, smart contracts. And we're here essentially to, prepare you to jump on this train of exciting journey to Web3. And last year we were kind of like finding our way around, setting up the society, But this year we decided to focus on actually building up practical skills of our members and help to educate the community about what the heck blockchain is all about. So, before understanding the blockchain, it's very important to understand, all the theoretical concepts behind it and the history behind it. And you'll be surprised that, blockchain concept actually came up in papers and research before 2009 or 2008 when Bitcoin white paper was released. And this year we're also launching a couple of other interesting projects. So some of them is a research project led by Ibi, who's currently in the room. And if anyone interested in participating in this research project or exploring it further, just speak to Ibi. And the idea is that we want to run this kind of an open format and open to students from any background. But essentially, it's going to be an improvement over Ibi's third-year project, research project on portfolio management with Ethereum. Am I right? Yeah. And I'm already in contact with a couple of people from different VC funds and protocols who are already interested in potential outcomes of this project. And the idea is that, it's something like some sort of a product to society, something for you to explore, to apply your knowledge and share expertise with each other. Now, moving on to actual blockchain course. So the motivation behind it is that I attended Polkadot Blockchain Academy this summer in Cambridge, which was basically, organized for the purpose of preparing the talent to enter Web3 job market. And some of the modules that you're going to see in this course are heavily inspired by some of the modules which were present in the Polkadot Blockchain Academy course. But I also thought that we really want to engage academics from UT Southampton because we've got so many great talents. We've got George, we've got cybersecurity research group, we've got a lot of interest from business school, and it would be nice if we, for example, put all those lectures together and kindly ask them to share their knowledge with you and in a more organized manner. So just a little heads up to set everyone's expectations right. You're not going to become blockchain developers after completing this course because it's going to be just 12 weeks, one lecture per week, and there's so much more stuff that's for you to explore. But the whole idea behind the course is to set you on the right path of exploring the space. So it kind of to get you started essentially. So what we want to do after this lecture potentially, if this is the topic that might be of your interest, that to go there and explore it yourself and potentially come back and share your findings with us. And then there's going to be different modules from targeting different aspects of blockchain. So this module is cryptography module, which is basically going to cover all the technical underlying foundations behind the blockchain, like hash functions, cryptographic functions, different encrypted storage solutions. The next module is going to be economics module, which is basically going to touch on game theory and why we have a cryptocurrency, why we have a currency in the blockchain system in the first place, what incentive it plays in a blockchain system, and why it's so volatile, and how it basically works together with socio-economic factors in our traditional financial systems. And then for the third module, blockchain basics, we're going to put the first two modules together, connect the dots, and actually move on to actual blockchain, explaining what what blocks are, why it's called blocks and chains. Again, how this related to smart contracts, what is different token protocols, and again, how they're all related to the concept that we introduced in the first two modules. And then on the fourth module, which is probably going to take place in the next semester, we're going to provide some hands-on experience and help you to potentially develop your own blockchain using a blockchain development framework called Substrate. Or if you want to target something else, we're also going to introduce you to a smart contract development. And after that, again, quite ambitious, but if things go well, we're going to put a hackathon together in collaboration with different universities for you to try out your skills. On the notes of collaborating with other universities, there's also going to be a conference next Sunday, 20th of November, co-organized with Cambridge Blockchain Society, Oxford Blockchain Society, and all the blockchain societies across the UK in London, 10 a.m. It's mainly organized and sponsored by FTT DAO, and it's basically aimed at students who want to get into the space, want to understand how the space works. And the conference is going to feature representatives from some of the best and the most famous protocols like Polkadot, Starkware, I think Polygon, and many others. So I think they're going to release a new batch of tickets. I think 100 more tickets, like in the coming few days. So make sure you grab one. Again, it's completely free, but it's a great opportunity, and DSOC is going to be there. So enough of me talking. Now shall we move on to the lecture? And let's welcome George, a member of Cybersecurity Research Group, a PhD student, who's going to introduce you to the basics of cryptography and how this is related to blockchain. Thank you, guys. All right, let me help.
All right, so welcome everybody to the very first session of the Blockchain 101 12 weeks course. So just want to give a quick intro. My name is George Giamouridis. I'm a part of the Cybersecurity Research Group here at Southampton University. And I work there as a PhD researcher, and my research is related to cybersecurity in the blockchain networks. So however, today we're not going to talk about blockchain. We're not going to talk about cryptocurrencies. We are going to talk about cryptography. And why is that? Because cryptography is a fundamental component of blockchains, and you are going to realize that in the next lectures. So what we are going to do today is we are going to set the basics, so you will be able to attend the next lectures that they are entirely related to the blockchain. So these are the learning outcomes for today. So we are going to start by explaining what cryptography is. So in the end, you will understand what are the main concepts of cryptography. Then we are going to explain some basic properties of cryptography. And in the end, you'll be able to see and tell the differences of symmetric and asymmetric cryptography, which are two different ways of encrypting data by using cryptography, of course. Now, very, very quickly, that's the agenda of today. So again, we are going to start by explaining what is cryptography. So we're going to give a definition of cryptography. We're going to see why do we want cryptography. Then we are going to see what are the hash functions. We're going also to talk about some properties of the hash functions. And then we are going to see how encryption works. So we're going to see how asymmetric cryptography and symmetric cryptography works. And in the end, we are going to explain some basic encryption functions. So before we start, I just want to go through some historical data, because a very, very common mistake is to connect cryptography with computer science, with algorithms, with hackers and stuff like that, which is something very, very wrong. Because cryptography started ages ago, and if we go back to 1900 BC, in Egypt, some explorers found the first evidences of cryptography. So what they found was some symbols written on some pieces of paper. So this was like the first evidences of cryptography. So we realized that people used cryptography even those years that computers weren't exist. Then in 100 BC, a Roman emperor called Julius Caesar was the first man created the first cipher. So he created a cipher, the well-known Caesar cipher, and he used this cipher in order to send encrypted messages to his army generals. Now, in the 16th century, a guy called Vigenère designed the first cipher, and he also came up with the idea of using what we call a cryptographic key. So he created the Vigenère cipher, which was the first cipher using a key, a cryptographic key. Now, after the 16th century and the 19th century, Edward Herben, this was a German cryptographer, he came up with the idea of the rotary machine. And after that, the 19th century, another German cryptographer, Arthur Serbius, I don't know if I pronounce it well, invented the well-known Enigma machine, which was used for sending by the Germans for sending encrypted messages during the Second World War. Now, after all these things, in the early 70s, IBM's customers keep sending requests to IBM because they were asking more private and secure communications. So IBM, there was a member of IBM, there was an employee of IBM called Horst Fistel, who started a crypto group, the first crypto group. And in 2000, the NIST, the National Institutions of Standards and Technology, started receiving applications about academic papers that they were related to cryptography, privacy, and everything related to encryption and stuff like that. So in 2000, NIST accepted an academic paper, a proposal by Riesendal, who was actually the proposal for the first cryptographic algorithm named AES, or Advanced Encryption Standard. So this was the first encryption algorithm ever created officially. So this was a very brief introduction to cryptography. So just to make sure that cryptography started ages ago and is not entirely related to computers and algorithms and stuff like that. Now, let's start talking about cryptography. So let's give a definition of cryptography. So what is cryptography? So we can say that cryptography is a series of techniques that we use in order to ensure that our communications remain private, remain secure. And this has different applications. We can apply cryptography from a network perspective, or we can apply cryptography for the storage perspective. But the question here is, why do we need cryptography? Why do we need to use cryptography? So unfortunately, communications, our communications when we use the internet are insecure and then can be intercepted. So what do we need? We need a way to ensure that even we communicate through the internet, our communications remain secure, remain private. There is another cryptographer, mathematician actually, Kirchhoff, who said that we don't really, security should rely on secret methods, but rather on secret information. And what does that mean? That means that people don't need to come up with new technologies. We don't need to reinvent the wheel. We don't need new things. The only thing we need is to use what we already have. We need to use the technologies we already have and apply something in order to make them secure. So we need some ways to make data within those technologies secure. Now, according to that, cryptography has too many applications. So we have cryptography, we have the end-to-end encryption, which is widely used in text applications. We have cryptography when we store data. So for example, you can store your data locally and encrypt them. And we also have cryptography for storing passwords. So as we are going to see later on, when you store some passwords in databases, we don't store them in plain text, but we store them in hash functions. And we're going to explain later on what hash functions are. Right, so let's get started with hash functions. So first of all, what is a hash function? So the hash function is a cryptographic function. So we use this mathematical function, which is used to encrypt some data. So what the hash function does, it converts data in a fixed size, in some other fixed size data. And this is a way to create unique fingerprints. And the output of the hash function, so the hash functions have inputs and outputs, and the output of a hash function can be called either hash value or hash code or digest, or what we use, the most popular one is hash. So when we say hash, we mean the output that a hash function produces. Now, let's talk about the properties of hash functions, because we said that hash functions are mathematical functions, so there are some properties. The first hash function property is called determinism. And when we say that a function is deterministic, it means that no matter the size of the input we have, we always get the same size of output. So let's write some things on the board. Right, so let's say, for example, that this is our hash function. So we said before that the hash function is just a mathematical function. So this is hash function h. And it has an input, and it produces an output. So I will call it output. So the determinism says that, again, no matter the size of the input, the output remains the same. So even if my input is this word, or my input is this word, which is longer, I will get the same size of output. So for example, I will get, let's say, for example, a 32-bit output. So that's what determinism says. And can anybody think a non-deterministic function? Any examples of non-deterministic functions? Something very simple.
Square root of number.
Exactly, square root of number, yeah. So a non-deterministic function, for example, would be, so this f of x will give me y, but if I use f of x, sorry, f of z, I'm gonna get something else. Let's say q. So this might be a different size, and this might be a different size. So these two functions are not deterministic. Now, right, moving on, the next hash function properties is called pre-image attack resistance. So we say that all the hash functions are pre-image attack resistance. And what does that mean? That means that if I get the output of a hash function, I can never, it's infeasible, mathematically infeasible, to go back to the input. And this is why we say that hash functions are called one-way functions. So I can go from, let me just do it again. So I can get the output. So let's say, for example, I have access to the output, which is the hash, but I cannot use the hash in order to go back to the plain text. This is what we call a one-way function. Now, the third property is called second pre-image resistance. And this is actually a property says that if there are two different inputs, it's always infeasible to get the same output. So again, I'm going to use these two words. So given those two inputs, you see they're different, I can never get the same output. So from the perspective of maths, we say that if given two different inputs, so x and y, there cannot be any hash function that produces the same output. So this is the third property of hash functions, the second pre-image resistance from a mathematical perspective. So again, for two different inputs, there is no hash function that produces the same output. So these are the main properties of the hash functions. And according to these functions, to these properties, sorry, hash functions have different applications. We can represent large data. So, for example, we use in cybersecurity, we use hash functions in order to get the checksum of a file and then check if this file is malicious or not. We can also use them for keys in databases, so we can represent data with hash functions. We also use hash functions in order to create digital signatures. So as you will see in the next lectures, when you will talk about blockchain, you will see that blockchain networks use hash functions in order to sign transactions. And we also use hash functions for key derivation. Now, these are some examples of hash functions. We have MD5, which is like the most popular one. We also have SHA. There are a couple of versions of SHA hash function, and the SHA-256. I just want to mention that this one is used in the Bitcoin, so you're going also to see that in the next lectures, and a couple more hash functions. So let me show you actually how a hash function works in practice. So if you just go online and just type SHA-256 online, you will see there is this very useful tool. So there are two text inputs. On the first input, you can just write your input. So a simple word like Southampton. Whoops. And as you can see, it will give you the output, which is the hash value. But remember what we said before. We said that each input has a unique output. So even if I make a small change to this word, so even if I change this letter with this one, you will see that the output changes. So even a small change in the input changes the whole output. Now, back to the slides. Right, so these are the hash functions. Again, you're going to see more details about hash functions when you talk about blockchains and digital signatures and private keys and stuff like that. So let's now talk about encryption, because encryption is actually the principal application of cryptography. And why do we need encryption? Why do we use encryption? So we use encryption because we want to make our communications secure. We want to make our communications private. So encryption is a technique of making data private and secure. So, where is it? Well, so let's talk about encryption and what are the components of encryption. So the encryption uses something which is called cipher. So the cipher is nothing more than an algorithm. So let's say that this is our cipher. So this is an algorithm, just that, don't need to say anything else. And it also uses an input, which is called plain text, and apparently produces an output, which is called cipher or ciphertext. Let's call it ciphertext. And also, ciphers use a key. So the key is a very unique kind of data, which is used in order to encrypt our plain text. So the whole process, so not the whole process, I mean, yeah, the whole process is given an input, the cipher will use the key and the input in order to produce the output, which is called ciphertext. So it turns out that there are two different methods used by ciphers. And the first method is the encryption, where encryption is turning the plain text into the ciphertext, so encrypting the plain text into ciphertext. And there is also the decryption, which is turning the ciphertext, going from the ciphertext back to the plain text. And for both of them, both for the encryption and the decryption, we need the key. If we don't have the key, we can't decrypt, we can't encrypt. Now, there are also two different methods of encryption. The first method of encryption we're going to talk about is called symmetric encryption, and symmetric encryption uses the same key for both encrypting data and decrypting data. On the other hand, asymmetric cryptography, which is the second method of encryption, uses different keys. So we don't use just one key, we use two different keys, and we're going to see how that works. So let's start with the symmetric encryption. So the symmetric encryption uses a cipher and a key. So the key is the same for the encryption and the decryption. So as you can see in this illustration, there is a plain text. This is the message we want to encrypt. We use the key, which is the same both for the sender and the receiver. And by using this key, we use the cipher in order to encrypt the message, and we produce the ciphertext. And then the receiver will receive this ciphertext, and with the key, which is public, is going to decrypt the message. So both the sender and the receiver use the same key in order to encrypt and decrypt the message. A very, very popular symmetric algorithm is the Caesar cipher. And we talked about this one in the first slide when we start talking about the historical data of cryptography. So let's see how the Caesar cipher works. Right, so again, very simply, the Caesar cipher is a symmetric encryption method. So it uses a cipher, as we said before. Actually, yeah. And what this cipher does, so this cipher takes the alphabet, so takes like A, B, C, say D, and so on. And it also takes a key. So let's say that our key is number 2. So it takes a key, so it takes an integer as a key. So it can take 1, 2, 3, and so on. So for this example, our key is number 1. Now, it also takes an input, the plain text, as we said before, and it produces an output, the ciphertext. Let's say that we want to use the Caesar cipher in order to encrypt the word, I don't know, good. Right, so we want to encrypt this word here. Now, when we use the Caesar cipher, this will take this word and the key too, and it will convert, and it will use this algorithm So the letter G will become I. The letter O will become Q. Again, Q. And this will become F. So again, we used key number 2, and we just forward each letter by 2. So G became I, O became Q, and D became F. So in the end, my ciphertext, the encrypted message, will be that. So the sender will forward this text, this ciphertext, to the receiver. So even this communication is intercepted, no one will be able to understand what does that mean, because it's encrypted. Now, the receiver, when the receiver gets this message, is going to use key number 2, and they're going to do exactly the same process, but now they're going to go 2 letters back. So it's going to convert I back to G, Q back to O, F back to D, and the initial message, the plain text, is going to be revealed. So why this ciphertext is insecure? What do you think? Any ideas why ciphertext like encryption algorithms like the Caesar cipher are insecure? Exactly, it's reversible, but why? Why is it reversible? Okay.
Puts it back into the same, thingy algorithm, then you can get the original back.
Exactly, yeah. So the problem here is, of course, the algorithm is reversible, but the problem here is that the key is very easy to be guessed. So you can easily guess the key because it's something very simple. You can create a very small script, 3 lines of code, which is going to try different numbers, and in the end, you will come up with a key. So it's a very simple key, and simple keys make algorithms insecure. So this was symmetric cryptography because, again, we use the same key for encrypting and decrypting messages. Now, asymmetric cryptography is slightly different because we use more than one key. And in asymmetric cryptography, we actually use 2 different keys. We use a public key, which is used for encrypting messages, encrypting plain text, and we use a private key for decrypting messages. So this is quite self-explanatory. Public keys are public, so anyone has access to those keys, anyone can use them. However, private keys must remain secret because if your private key is revealed, anyone will be able to decrypt messages, and you don't really want that. So this is how asymmetric cryptography works. So let's say, for example, that we have user A and user B. They want to send a message to each other. So user A wants to send a message to user B. So the user A will produce a pair of keys, a public and a private key, and user A will send the public key to user B. So the user A will also send the message, the encrypted message, to user B, and user B, because user B has a private key and the public key of user A, will be able to decrypt the message. So if someone gets the private key of user B, then this person will be also able to decrypt what user A has sent. So that's why we say that private keys must remain secret. And yeah, in this illustration, you can see how asymmetric cryptography works. It's just this process that we explain. Now, asymmetric cryptography is used in blockchain. And in this slide, I will explain actually how asymmetric cryptography is related to blockchain, but I'm not going to give more details because this is not the topic of the day. So how asymmetric cryptography is used in blockchain? So just very quickly, in blockchain, we have different blocks. We have blocks, and blocks are connected to each other. So as you can see in this illustration, blocks are connected to each other. So each block has a child, and the child is connected to its parent. So we see block 1 has a child, which is block 2. Block 2 has another child, which is block 3, and so on. So the way those blocks are connected to each other is based on the hash functions we explained before. And that means that if I make, remember what we said before, if a small change in the hash function in the input changes the whole output. So imagine that you make a change in block number 2, every block after block number 2 will change. So that's because all the blocks are connected to each other through the hash functions. And again, you're going to see more details about how these things work in the blockchain sessions. But that was a very, very quick introduction why and how we use asymmetric cryptography in blockchain. Now, let's set some considerations about asymmetric and symmetric cryptography. First of all, symmetric cryptography is faster, right? Yeah, of course it's faster because you use just one key, so we don't need to generate more keys. We don't need to find ways to share those keys. But the problem with symmetric cryptography is that the ciphers we use in symmetric cryptography are insecure. And we saw an example before, because keys are very simple, they can be, anyone can guess the key and intercept the communication. So that's the problem with symmetric cryptography. The problem is trust. On the other hand, asymmetric cryptography is slower because you need more things. You need to generate a pair of keys, you need a private key, you need a public key, and there are some ways you need to follow in order to share your public key. So we call them public key. I mean, there are different ways you can follow in order to share your public key with others. And there is no problem regarding security. It can be slower, but asymmetric cryptography is safer. And this is why it's also used in blockchains. Now, both asymmetric and symmetric cryptography can be used in parallel. So there are different systems that they use hybrid cryptography, and that means that they use both symmetric and asymmetric cryptography. And a very good example is HTTPS. And HTTPS uses asymmetric encryption in order to transfer symmetric keys between the users. So yeah, these are some considerations. Again, symmetric cryptography, faster but less secure. Asymmetric cryptography, slower but more secure. But they can also be used together, and we call that hybrid cryptography. So let's just do a quick recap. So yeah, we started by exploring how cryptography started. We said that cryptography is not entirely related to computer science, is not entirely connected to computers, to hackers and stuff like that. Instead, cryptography started ages ago. We gave a definition about cryptography, so we saw what cryptography is and why do we use cryptography, because we just want to find some ways in order to secure our communications. We want to make our communications more private. And cryptography, we also saw that cryptography can be used from a network or a storage perspective. We said also that we don't need to reinvent the wheel. We need to use already existing technologies, but what we really need to do is to make them more secure. Some applications of cryptography, there are more, but these are some examples. And then we introduced the hash functions. So we also saw the most common properties of hash functions. We said that hash functions are deterministic, which means that it gives me, given an input, I'm always getting the same size of output. The second property was the pre-image attack resistance, which says that if I get the output of hash function, I can't get back to the input. And we said that those functions are also called one-way functions. And the third property is the second pre-image resistance, which says that two different inputs can never give me the same output. Again, we saw some applications of hash functions, and we said that hash functions can be also used in the blockchain networks. We gave some examples of hash functions, and we then start talking about encryption methods. We saw what is a cipher, the components of a cipher, and we also saw what symmetric cryptography is and asymmetric cryptography is, where symmetric cryptography, we use just one key, while asymmetric cryptography, we use a pair of keys, a public and a private key, where the public key is actually the one used to encrypt data, and the private key is the one used to decrypt data. Again, we said that asymmetric encryption is used in the blockchain networks, and you're going to see more details in the next lectures. And we set some considerations. Again, we said symmetric cryptography is faster but not much secure, while asymmetric cryptography is slower, but we trust it more because it's more secure. But again, they can both be used in parallel, and we call this hybrid cryptography. So this is some additional reading if you want to see and find more details about cryptography or hash functions. And I think, yeah, that's pretty much for me. So thank you very much for your attention. If there are any questions, just fire me with questions. So yes, thank you very much again. Yeah. Yeah, go on.
One of the properties of the asymmetric encryption was the second pre-image resistance.
Yeah.
And isn't it true that there is a concept of hash collisions where there have been instances where it is possible for hashes to have the same
Right. Of course, yeah. So yeah, the question is regarding the second property of hash functions. Because we also, yeah, this one. We say that those functions are collision resistant. So the question was, is there any chance to get the same output, the same hash value? The answer is yes, but the chances are there. I mean, there is no chance to get that. It's almost infeasible. I won't say entirely feasible, it's almost infeasible. But this never happened, and it's something very difficult. I mean, if you use a simple computer, and I mean, if you write a script which will try to do such thing, to find a collision, you won't be able to find something. But if you use a quantum computer, you might be able to find something. But again, you will need time, a lot of time. But yeah, I just forgot to mention that, yeah, this property, the second pre-image resistant, we also say that hash functions are collision resistant because it's almost infeasible to get the same output given an input. Yep. Any other questions? No. Okay, cool. Thank you very much again.
Any questions for me, guys?
Ah, yeah, the mic.
So, yeah, thank you, George. Excellent presentation. Again, any questions regarding the society, regarding the course, the conference, the future plans, your potential involvement, far away. Again, let's keep it just casual, you know, yes?
What was the conference you said it was in London on 25th of November?
So the question is, when is the conference? It's 20th November, so next Sunday. Yeah.
The name of the conference.
It's Blockchain Applied. It's organized by FTT-DAO, and it's also published in our Discord. So if you're in our Discord, you go to announcements channel. We also announce the conference, and also with regards to the course, we're going to post all the updates and future lectures. Usually, they're going to take on a weekly basis every Wednesday for the first module, and we still finalizing the arrangements for the second module, for economics module. We just, finalizing, confirm the availability of lecturers, because we're also going to have some guest lecturers for economics module. Right. Any more questions? Yes.
You mentioned before that next lecture sessions will be more technical, so you're going to
Right.
write code and stuff like that. Is there going to be a public repository, maybe something like that, where you will share your code, and so everyone can get access to that?
Okay. So the question is, I mentioned that next session going to be more technical. Is there going to be a public repository where you're going to find the resources? I already published the link, a GitHub link, an announcements channel in Discord with our public repository where you're going to find the course notes for the lectures, and we're also going to upload the slides. And okay, also the idea behind the course is also to have some hands-on experience. So potentially the next lecture, the lecture after next one, you're going to have a small coding exercise where you're going to play around with hash functions using programming language Rust, because that's the programming language we're going to use for blockchain development. So if you want a little heads up, just start learning it right now. It's quite handful and commonly used in the blockchain space if you want to become a blockchain developer. With regards again to any course arrangements, if you have any concerns, if you have any suggestions, feel free to jump on Discord, drop a message, talk to me after. If you have any ideas or some projects you want to do, again, we are here for you exactly for that reason, to facilitate. And as I always say, the whole purpose of the society is to connect enthusiasts with professionals. If you've got some cool project in mind, you want to talk about it, you're thinking how to implement it, even if you want funding, just come and talk to me, because that's what we're here for. Yes, that's great.
Is it still possible to get a ticket to the conference somehow?
That's a good question. The question is it still possible to get a ticket for the conference? Okay, so officially no. They're going to release, I think, 100 new tickets in the coming days, but I'm not sure. But we can do, if you decide to volunteer for the conference, to be a volunteer, you can get one ticket for free. So that's, I mean, the whole ticket's a... Pardon?
Is the volunteering option still open?
Yeah, volunteering option, like basic...
What would be the responsibility as a volunteer?
Just basically jack of all trades. You just... you need to scan tickets, help around, set up equipment, again, volunteering.
You need to be there.
Not from, yeah, from 6 p.m. till 6 a.m., yeah. Right. Yeah, again, we've been asked to send some volunteers from our society, like every society has been asked to send volunteers. If you want to volunteer, it's also a great opportunity for you to network with people there. And nonetheless, if there's going to be, a new batch of tickets, I'm going to put announcements on Discord saying, okay, so if you haven't managed to grab a ticket, please do. Right. Any more questions? No? Okay, cool. So thank you for coming, guys. If you can do me a favor, spread the word, invite your friends, invite friends from different departments, because again, even though the cryptography module may seem a little bit like too much for you, like if you're from a non-computer science background, the next module will look too much for computer science students. That's the whole idea, is that we basically dive in deep, like in every single aspect, and the whole idea is to have people from different backgrounds and build this kind of platform for knowledge sharing. So essentially, I encourage you to find someone from different departments, talk to them. For example, EB is a perfect person to talk about anything related to blockchain from financial side. She posted an excellent article from Bloomberg on Discord. And JJ is one of the committee members, also published it. Yeah, I mean, just invite your friends, say, hey, like this, of course. Yeah, that's the only favor I ask. Okay, thank you guys. I'll see you next week.